from
Okay.
Tulane University, who will tell us about causal causality.
Okay.
Please go ahead.
Hi, everyone. I'm Sander Uijlen. I'm currently at Tulane, the group of Mike Mislov, working on categorical semantics of quantum programming languages. However, since I assumed the group here was mostly physicists, I decided to give a talk about something I did when I was still a PhD student in Nijmegen. This is joint work with Alex Kissinger. And it's about categorical semantics for higher order processes and causality. And I think that this quote, which is from a paper of Dusko Pavlovich, really says it all why categorical semantics are needed. So I do not want to go into category theory. And I've tried as good as I can to cut out all the mathematics here and still hopefully have a story to tell. But if there are questions, please interrupt me. I think that's better than waiting until the end. So while I don't want to do any real category theory, I do want to look at quantum mechanics. And with quantum mechanics, I really mean sort of the standard Hilbert space-like quantum mechanics. No like relativistic effects and Dirac equations. And I want to do this from a compositional view. I want to emphasize the compositional structure of quantum theory. And the way to do this is using symmetric monoidal categories. Now, what are they? Like I said, I don't really want to go into this, but basically we consider quantum systems, which are, for me, bounded operators on a finite dimensional Hilbert space. And then these are the objects of the category, in case you know what a category is. But if not, it doesn't matter. We consider quantum systems, and we consider operations between these quantum systems. So the goal here is not to consider a single system. The goal is to consider the relations between different quantum systems, which morphisms, which transformations, which operations between them can we consider. And a quantum operation is precisely a completely positive, and sometimes we also want trace preserving, but not always, completely positive maps. And these are precisely the maps which send states. And by states, I do mean a density matrix here, not a vector in a Hilbert space, but really the lifted to this operator algebraic sense density matrices. These maps send these states to states. And looking at quantum theory in this way allows us to use a diagrammatic language. So what does this look like? When we have a system and a quantum system, so this is a quantum system, can be anything, right? An electron or a photon or a pair of electrons. We draw a line and we give it a name A, and A is our system. And then we consider morphisms between these systems, and we just draw this as a box between these two lines. So, by the way, when I move my mouse, can you see this little hand?
Yes.
That I'm pointing. Okay, that's good. So we have these morphisms, and we just draw them as a line, and this is a completely positive, sometimes trace preserving map between the system A and the system B. And these maps we can compose either sequential, where we first do one map and then do the other. Or if we have two systems, we can put the systems next to each other. That's taking their tensor product, and then act on one system with one map and act on the other system with the other map. And this is a parallel composition of these maps. And then there is the tensor unit. This is the trivial quantum system or normal system. It is classical. So this is modeled by just the complex numbers. We draw this as nothing, just empty space. And then we have a swap, which is the symmetry in this term, symmetric monoidal category. Monoidal stands for this tensor product. Okay, we then consider special maps, namely those that go into or out of this tensor unit. And maps coming out of the tensor units are states, which, like I said, are density matrices. So this rho is a state on the system A. We have maps going into the tensor units. These are effects. These correspond to doing a measurement and getting a particular outcome. And then we have scalars, which are maps from the tensor unit to itself. And these will usually be probabilities. So this will be a diagram which has no inputs and no outputs. I'm going the wrong way. Well, using these ingredients, we can sort of just build general processes. We can have processes which act on like this composition of systems A and C to B and D, and then we can plug in a state and take one of the outputs and do some new process on that, which has an outcome. And the thing about these diagrams that makes them really nice to work with is that basically only their connectivity or their topology matters. It doesn't matter if this F is a bit more up or down, or if they're more spaced apart. As long as these diagrams are essentially the same, they represent the same morphism. Well, what else do we need in order to talk about causality? And that is a special type of effect, which is called the discarding effect. This is an effect which has nice behavior with respect to this tensor, So if I take the discard on a composite system, it's the same as discarding this system separately, and discarding nothing should just give nothing, one trivial thing. And this discarding effect is the trace in quantum mechanics. So we have this system, and we can think of it as like doing a measurement and forgetting the outcome, marginalizing over a certain system or a subsystem, or just throwing away the system that we have. And I would just want to say that looking at quantum mechanics in terms of this compositional structure, like, it is needed. If we can't do that, then we can't do any science, because whenever I do something in the lab here on Earth, I need to take into account the weather on Mars, because it's all sort of one system, which is the universe. I need to be able to look at subsystems, and I also want to know how things combine when I tensor them. Okay, using this effect, we can say when a process is causal. And for quantum mechanics, this is precisely when it's trace preserving. So we say a process is causal when, if the output of such a process is discarded or ignored or marginalized over, it doesn't matter which process happened. So we can say that effectively no process happened at all. And this implies that a causal process can only affect processes which consume its output, so which are connected to the output of this program. And this gives an idea of a causal future, which by definition is the processes. We can think of a process as a lab. There is a lab somewhere, and Alice or Bob does a certain process, and the effects, like the outcome of that lab, can go to a new lab, and that lab is in the causal future of the first lab. So as an example, we can consider a morphism like this, where we have two of these labs or two of these processes. And we now want to see what happens. So, and we say these, let's assume that these phi A and phi B are causal. If we then discard this phi B, the output of this phi B process, then because it's causal, this discard falls through. And we see that this B system is disconnected from the rest of the diagram. There's nothing going on here. So this B system cannot influence this A system. So there's no signaling from B to A. And we can say that this A system is in the causal path of this B system. Okay. We can do this with larger, with sort of multi-partite processes as well. We discard some outputs. We see which inputs can in principle affect which outputs, and this gives constraints on the causal relationships between these inputs and outputs, or as you may think of it, between these labs. For example, what we just saw is an example of a one-way signaling process. And that just means that if we discard one of these output systems, then the resulting process factors out as some process phi prime, which only goes from A to A prime, and the discard in B. So, and just like before, it says that the output of A does not depend on B. Another type of signaling constraint would be no signaling. And that is when there is one-way signaling in both directions. So we have this diagram, but also the sort of mirrored one, where if we discard the A system, then there would be a system phi double prime, such that there's sort of a mirrored version of this. Okay, if we have such a one-way signaling process that we had before, we can also use it to transform a process psi. So we take the output of this A system, we possibly do something with it, and then use this again as an input to this B system. So the whole thing sort of becomes a transformation of this psi. And we can consider this more general as we consider this sort of Pac-Man shaped map, a box with a hole in it here. And we can plug in a process, and the output is a new process. And if phi was from B to C, then this new process is from system A to D. So we get transformations of transformations. So higher order processes. But the thing is, these might not preserve this causality that we were talking about, the trace preservingness. Indeed, if we have some sort of a feedback loop like this is causal. If we discard the output, then by just looking at the topology, this is the same as just discarding. But if we input a process here, namely the identity, then we get this circle. And if you work out what this circle is for quantum mechanics, it's generally not causal. So this leads to a definition. A process, W, is called second order causal if for all processes, for all causal processes like this, plugging in this causal process into this second order causal process again leads to a causal process. So if for all causal processes phi, this map again is causal, then we say that W is second order causal. Well, this is a game we can of course play also with multiple inputs. And I'm going to take a slight detour to say something about an example which is called the quantum switch. So the idea is that we have some process which has an input x and it takes in a qubit. We have these two holes in which we can input processes from A to A prime and B to B prime. And there is just some overall input system C and an overall input system C prime. And now we call this map a quantum switch if whenever we input the zero state, we get something which effectively works like this map. And if we input the one state, we get its mirror image where, and now here you see this same map, but with these maps, phi A and phi B, sort of these labs plugged in. If we follow the line now, we look at this topology, we first see phi A, and then we see phi B. So if we input this 0, we compose these processes in one way. If we first input 1, then we see this mirror image, and we would first do phi B and then phi A. So there is a different causal order between these processes, phi A and phi B. This is interesting because we can also consider what if we don't just put in pure states 0 or 1, but we put in the plus state, which is a coherent mixture of 0 and 1. Well, if we look at what we would then get, we would get some coherent mixture between these two orders, phi A and phi B. So first phi A and then phi B, or first phi B and then phi A. And this has been done in labs. People have done experiments there, and they have obtained correlations which cannot really be described by a single causal order. So there's something called indefinite causal order going on here, which I think is very interesting, but I don't want to go into this right now. So what's going on here? Sort of a recap. This quantum category that we have of bounded operators on Hilbert spaces and completely positive maps, it cannot distinguish between this type of first order causality, which just send causal states to causal states, or this higher order causality, because they are not the same. That was this example for that we have seen. So there's a problem going on here, and we need to solve that. And the way to solve that is to construct a certain type theory for causal orders. So what we do is for every process, we say it has a certain causal order between its different inputs and output pairs. I'll give examples in a moment. But what we do is we get this we form a new category where our objects are now pairs of a quantum system and a set of generalized causal states on this system. So for example, I'll get to those examples. We get and morphisms need to preserve these generalized causal states. And when I say generalized causal state, I really mean that everything is a state. Maybe you've heard of the Joe Jamelkowski. So it has an L with a sort of a dash through it, but tech doesn't take this. I see. Anyway, there's a Joy-Jamelkowski isomorphism, which allows you to consider processes as states on a larger system. And this needs the dual, but I've decided not to talk about duals. So we get these sets of generalized causal states, and now we want morphisms which preserve these sets of causal states. So for example, a causal map sends a normalized state to a normalized state. That is our standard causal map. But for example, this switch map that we had actually sends any non-signaling process to a causal process. So it has the type of non-signaling process to causal process. And if I now have any type, I can just say, I take this type and I want to send it to some other type. And this gives me a new type of transformations between the types that I had. If we go do some mathematics on what kind of category this actually is, I don't know if there's people who have heard of these things, but the resulting category is something called an isomix star autonomous category. Don't really want to go into this now. I do want to give a couple of examples. So, like we have seen, we have these first order systems. We had these originally. These are just state spaces. And we still have these, and well, they're still just state spaces. We have their duals, and if we look at causal things, and this is only the discard map. We have causal processes. So these, well, we know what those are. These are precisely these trace preserving maps. We have their duals. These are maps which take in a causal process and then give us a number, but it has to be normalized, and then it follows that such a process always vectors as a state and then a measurement state, do the process, and then you do a measurement or you discard the system. There are more interesting examples. So any bipartite causal process can be obtained from causal maps. If I have the type causal maps from A to A prime, and I have the type causal maps from B to B prime, Then I combine them in a special way. This is called the par, and it comes with this star autonomous category. It's you can see it as the just like and or in classical logic have this sort of De Morgan dual to them with not. So not and not A and not B is not A or B, right? And this par has such a same relationship to the tensor and the dual. But we can construct all processes, all causal processes from these causal processes between A and A prime and B and B prime. We can classify the one-way signaling processes as maps like this, A to A prime to B prime. So this basically says, give me a state on A, give me a causal process from A to A prime, then the output will be something of type B prime. And these things all factor in quantum mechanics as these type of one-way signaling maps. So I plug in a state here, I take my causal process from here to here, and the result, this whole thing, is a state on the output system here. We can also obtain the non-signaling maps as from the types of A to A prime, tensor the types of B to B prime. So if I have my state space, sorry, my causal process state spaces, generalized state spaces, I can combine them in two different ways, namely using this tensor or the par. And the par gives me all processes, and the tensor gives me only the non-signaling ones. And then there is a calculus involved with these maps, and we can, for example, show that there are embeddings of no signaling maps into the one-way signaling maps, which embed into the bipartite processes. And then finally, I can again take like a dual of these non-signaling maps, and then you get something again, which is basically this quantum switch. If there were no input and output here, we take this to a probability, and the switch has an input and output, but that doesn't really matter. And we can go more general, right? We can look at maps which take bipartite causal processes to non-signaling processes. We can just create this whole zoo of different types. I think that's about it.
All right. Thanks for your talk. Are there any questions for Sander? We have a few minutes.
Sander, I have a quick question. So, why was it useful for the whole project to use those graphs instead of just like writing down the equations and do partial traces, etc.? Like, did you get extra insight from drawing these graphs?
Yes.
Can you elaborate on that, please?
Yes. So take this. Okay. So first of all, I would say that drawing these diagrams makes life very easy. There are a lot of equations which become tautologies because the diagrams are the same. I think a good example is if I if I have 4 processes and I first parallel compose 2 of them, and I parallel compose the other 2, and then I sequentially compose those 2 composed processes, or I first sequentially compose 2 processes and I sequentially compose the other 2, and then I parallel compose them, that is the same map. It's sort of a block. If 2 lines with two blocks on each line. And the fact that these are the same in diagrammatic terms is really a tautology. It's exactly the same picture. Whereas if you write the diagrams, if you write the equations, you need to do well, at least some work to show that these are the same. A perhaps better example, and this is really where you get some intuition from, is if you start looking at these jewels of non-signaling matrices, such as this W. You can now start playing with what happens if I input a process in only one of the holes. So I input a process here. All of a sudden, this whole map becomes well, a process which has only one hole in it. We know that this one hole, like this bottom one, this one hole thing decomposes as a state and a discard map. So we fill this in back here again, and we find something that relates to this process which we put in here. And if you then put in a swap map here, for example, you can say certain things about the nature of these so-called W matrices, or process matrices, they're sometimes called. It's quite a bit of literature on these things.
I see. Thanks for the clarification. It's much clearer now.
Also to prove, just proofs that you indeed have a star autonomous category, that this construction works. They become much easier using diagrams.
Mm-hmm. Mm-hmm. All right. Yeah. Thanks for that.
Right. Thanks for that. I have questions also, but I think we need to transition to the next speaker.
Okay. Well,
Right.
I'm available if anyone ever wants to, not now, but in the break or after another day.
I'll write you
I'll
an email.
gladly talk a bit about this stuff.
Yeah, I'll write you an email with my questions. All right, so I think our next speaker is Peter Bierhoff.